So radioactivity, people are generally have negative feelings about radioactivity, right? So it can hurt you, it can kill you. But radioactivity is actually natural. It's a natural component in the environment. And our bodies have adapted to survive in this naturally radioactive environment. Where does the radiation come from? Well, small amounts of it come from outer space and penetrate through our atmosphere. But our Earth also contains radioactive elements. All of the elements beyond atomic number 83, which is bismuth, are unstable and thus are radioactive. So when we look at the periodic table, you've got bismuth there is number 83, polonium is 84. And if you look at the atomic numbers after 84, they're all whole numbers in parentheses. And that's because those guys are all radioactive. Some elements that are smaller than bismuth are radioactive as well. Radioactive nuclides decay at different rates. So decay is when that particle is emitted, and that atom has changed into a different element, and so then the amount of the original element is continually decreasing. So half-life is the time it takes for half of the original sample of the parent nuclide to decay into daughter nuclides. Now, this is an exponential process. After one half-life, you have half of the substance left. After another half-life, that half is cut in half. So now you've got a quarter. And it just keeps getting cut in half. It's not that you have two half-lives and it's all gone. It just keeps getting smaller and smaller. So after two half-lives, you've got 1/4 of the original sample. After 3 half-lives, 1/8. After 4 half-lives, 1/16, then a 32nd. It just keeps getting cut in half. Some nuclides decay very quickly. They have very short half-lives. Those are very active. They have a large number of decay events in a given unit of time. And we define decay event as being the emission of radiation by a single radioactive nuclide. So one atom emitting its particle, that's a decay event. So radon-220 has a half-life of approximately 1 minute. So that's short. So if you had 1 million radon-220 atoms, after 1 minute, you'd only have 500,000. And after another minute, you'd only have 250,000. So after 3 minutes, you've only got 1/8 of a million. Okay, so it goes down very quickly. Thorium-232, much less active, its half-life is 14 billion years. So that obviously has a lot fewer decay events per time. In a minute, there probably will be no decay events, right? Because it takes 14 billion years for half of the sample to go away. So here's a graph showing that. Here we have the number of atoms present in millions and the years in billions. So 40 would be 40 billion years. So if we're starting with 1 million atoms, after 14 billion years, the half-life, now we've got half of a million. After another 14 years, another half-life, this is cut in half again. Another 14 years, it gets cut in half. Another 14 years, it gets cut in half. So as you keep going, the changes get smaller and smaller and smaller. Eventually, you would get to one atom, and when it decayed, then it would be all gone. But that's way, way out there. Because in terms of numbers of atoms, 1 million is not very many. Right? A mole, 10 to the 23rd atoms, is the size generally that you can hold in your hand, a small but visible amount. And so that's a lot more than 1 million. The half-life is unique to the nuclide, and it has nothing to do with physical conditions or the chemical environment. You can't change the half-life of a given isotope. It just is what it is. So here's just some examples. Thorium, uranium, carbon, radon, thorium. There's two different thoriums here, 232 and 219. They have very different half-lives. Thorium-232, 14 billion years. Thorium-219, 1 microsecond. And the types of radiation are given here. So we should be able to do problems like this. A radium-226 sample initially contains 0.112 moles. How much radium-226 is left in the sample after 6,400 years? The half-life of radium-226 is 1,600 years. So these problems will be set up so that we don't really have to do math. We don't need to use exponents. I mean, there's a little math, but it's just cutting things in half. So this is how I would recommend you do a problem like this. Our initial sample size is 0.112 moles. So that's what we're starting with. And so we're just going to go by half-lives and see what happens. So one half-life is 1,600 years, and now, I'm not going to trust my head to do that math, 0.112 divided by 2. 0.056. So that's 1,600 years. Okay, so we're trying to get to 6,400. So another 1,600 years. Now we've got a total, so this was 0, this is 1,600, and over here now we're at 3,200 years. I'm going to take that 0.056 and divide by 2 again. 0.026. No, 28. Can't read. Moles. Do another half-life. So 1,600, that would be 4,800 years. And we divide this into again, so 0.014 moles. We're trying to get to 6,400. So another 1,600 years gets us at 6,400. And we'll cut that in half one more time and 0.007 moles. So there's numerous ways to arrive at this answer. I think this is the most intuitive, straightforward way. We don't have to do any big math problems. We want you to understand the concept of half-life. So every half-life, you cut the number of particles in half. Since the number of particles is directly proportional to the mass, it also is cutting the mass in half. Any questions about that one? So the naturally occurring radioactive elements, the ones that we find in the Earth, are either have very long half-lives. They've been here since the beginning, whatever that was, whatever you believe about that. Or they're being continually formed by another process. So uranium, atomic number 92, that's the heaviest naturally occurring element. Uranium-238 will decay to thorium-234, and the half-life there is about 4.5 billion years. So it's going to take a very, very long time before all of the uranium-238 has decayed. As that decays, it forms thorium-234. So thorium-234 is slowly but continually being formed. Thorium-234 has a much shorter half-life. It's also radioactive. It decays with a half-life of 24 days. So if you had a fixed amount of thorium-234, it would completely decay in a reasonable amount of time, right? The half-life's only 24 days. But there is always thorium present because it's continually being formed from uranium-238. So, blanking on what PA is. That's embarrassing. Can't remember what it is. Oh well, PA-234, the product of that thorium decay, also radioactive, decays to uranium-234, different uranium, and this half-life is 244,500 years. Well, the uranium-234 is also radioactive and decays, and so this process goes on and on and on. They're just changing from one radioactive thing into another. One of the things that's formed in this long process is radon gas, and ultimately it ends up being lead-206, which is stable. So all of the uranium-238 present in the environment is slowly decaying away through this long process to lead-206. All of the nuclides in that decay series are present in the environment in varying amounts because they're continually being formed and they're continually being decaying to other things. So this is an illustration of that decay series of uranium-238. So starting up here with uranium-238, and alpha emission to form this, beta emission, alpha, alpha, alpha. And so we see that sometimes the atomic number goes up, sometimes it goes down, and the end result is lead-206. But all these other things are continually being formed and decaying in the process, all natural. Just because something is natural does not mean it's good for you.